Okay, so now we are talking to Chris Gilly, who is a graduate student at CU Boulder studying waves that help heat the outer layers of the sun to millions of degrees. He is also interested in the sun Earth connection and how what happens on the sun can affect us here on Earth, for good or ill. Gilly looks to use new technologies like the Parker Solar Probe and the DKIST telescope to further his work. Hi, Gilly. Thanks for being with us.
Thank you so much. Yeah, I'm glad to be here.
So to start things off, well, I'm going to go ahead and reference something from your website, which, by the way, can be accessed through the CU. If you just search like colorado.edu space Chris Gilly, you'll get his website. It'll pop
You
up
can also
there.
go to gilly.space, just gilly.space. Type that into your bar, and that's me. Yeah.
That's so easy. How did you get a dot space suffix?
$20 a year.
Wow,
The
that's
dot space
amazing.
domain. They've actually opened up all kinds of cool domains. One of them is .sun, but because of Sun Microsystems, that's actually very expensive of a domain to get.
Sure,
So I got
sure.
.space.
Gilly.space. That's perfect. That's super easy. That's GILLY dot space. So
Sure.
on your website, on your website, Gilly, you mentioned that you study the way that light from the sun affects the rest of the solar system. Are you looking at, and obviously I don't want to like, say that you're lying on your website, but are you talking about light itself or other stuff that is associated with the sun, say the charged particles that we talk about, or, like coronal mass ejections? What are you looking at as far as stuff from the sun affecting the rest of the solar system?
Yeah, so I study light. I did a lot of light research in undergrad as well. And in general, I just really like photons and how they work, how light works. Trying to imagine yourself as a photon traveling through space is, it's really wild, the consequences of that. So I'm interested in light. I understand light more than, probably more than I understand like plasma and stuff like that, honestly. But you're right, the actual light going out and affecting the solar system. I've written down a couple different ways that it does, some cool examples, but really I'm using light to understand the sun. And so, I mean, a lot of people do that. You look at the sun with a camera or a spectrograph or something, you get that light and you try and interpret it. But I would say like, I'm really working on the, how does that interpretation work? If I measure this, what does it mean? There are some like basic steps that people take, like, oh, if I measure this, that means maybe it's so hot, it's this hot. But that process of going from I've measured light and now I'm trying to say something about the sun, it's rife with pitfalls. There's a lot of things you can do incorrectly, and you'll get a result that might not actually represent what's happening on the sun. So a lot of what I do, the title of my research is like optically thin radiation is what I study. And so if you look around me right here at this sun picture, right, like the sun itself is opaque. You can't see through it. But when you look up here in the upper regions of the sun, it's the atmosphere. Just like air, it's not opaque. And maybe light's coming from it and scattering off of it. But when you look over the surface of the sun, you're looking through a whole long column of plasma. And like when you see this stuff right here, like that's probably happening. Is it in the foreground? Is it in the background? Where's that going on? There's a lot of interpretation that has to be done there.
I have a lot of friends that would be really happy with you right now because a lot of my non astronomy friends often kind of, get on me about, well, how can you possibly know what's really going on in the sun? Like you say, you can, take these measurements or do these computer simulations. So it is really cool to hear that you're studying that process of, okay, we have this data, the raw data. How can we trust that process and develop it so that we know that our conclusion is really sound?
Yeah,
So
and that's been a theme in my research for a long time, even in undergrad. I'm really interested in the measurement process and trying to get that. And like my research really does focus on light and measuring light either with images, sort of like this image here, or just taking like the color of the light and looking at it very closely. But there's lots of other kinds of measurements that can be taken by this of the sun. We recently you mentioned the Parker Solar Probe. You know, um, the Parker Solar Probe is an instrument that we recently launched a couple years ago, and it's already been around the sun a couple times, and it has all these measurement instruments on it. So it's not just using telescopes, it's got particle detectors and magnetic field detectors and all these things. And an example I like to give is, like if you look across a room and you see a sandwich sitting on a table, you might be able to know what kind of sandwich it is if you look really closely, but you won't be able to tell all the toppings that are on it. You won't really be able to know if it's tasty, maybe it's too salty. To know those things, you really have to go and pick up the sandwich and take a bite out of it. And so that's like what we do with a lot of what are called in situ instruments. We send a spacecraft out into space, and it's right there in the meat of it, measuring locally. And that's really cool too. Those instruments are also hard to interpret data from, but maybe a little bit easier in some ways. You don't have to try and pick out stuff from an image. You can really say, I measured 6 particles of oxygen here. But again, all instruments, if you measure 6 particles, did 100 particles hit the instrument and you only measured 6? What's your efficiency like? All those kinds of things. There's a lot, when you take a picture with your cell phone camera, you're not like, oh, was that thing really blue or not? It probably accurately did that, but like, it might be doing a lot of magic processing. And really, when you took the picture, that flower was actually a little bit more like purple or something. It can change in the measurement. And if you just look at your measurements, and you don't try and like figure out that interpretation, you can think that really that sunset really was that way oversaturated sunset, when in reality we know that Photoshop was probably used to enhance that image.
Well, and I imagine that, these kind of in situ measurements of sending a spacecraft to, say, the sun and getting these, measurements that you can't get unless you're right there, even if we haven't yet developed the techniques to fully understand and break down what we've taken, now that data exists. So that when scientists do figure out exactly, the best method or the preferred method to, analyze some data set, it's available to them right away. You don't have to say, okay, now we have this process, let's put together a spacecraft and maybe in a decade we'll get this information.
Absolutely. And the that process happens at all stages. Like right now, the DKI solar telescope in Hawaii is it's not even functional yet. Like it's almost there. But I mean, the past 5 years of my life, you hear about it all the time. Oh, when DKIST opens, we have to make sure that we have the calibrations ready. When it gets ready, we have to make sure we know how to do spectral polarimetry is a buzzword right now. So what was I talking about? Yeah, so yeah, the DKI Solar Telescope, which is named after this senator. No, let's start over. Yeah, so in the past several years that I've been working on solar research, there's just been this big push to try and understand the instrument before it gets started. But on the other side of things, we launched the Solar Dynamics Observatory 10 years ago. And they tried to do a lot of calibration of that instrument beforehand. But once it got into space, they also had to recalibrate it. Did anything change in launch where the mirrors adjusted slightly? And then over the past 10 years, I mean, this thing's been staring at the sun. Sun's bright. And that ends up degrading the instruments a little bit over time. So they actually have to recalibrate over time to make sure that they're still getting the correct results. And then, even further than that, one of my first research projects ever was to reanalyze some data from Voyager. And this was data from like 1977 to 1995 or something like that. And yeah, I reinterpreted it using a slightly different model for one of the instruments, dispersion, one of the instruments, because it changes over time and we learn new things. So yeah, the process of calibrating and maintaining the calibration of an instrument is long. It's not just one thing that you do. And honestly, every time you interpret a result, you go through that process and make sure that it's done each time.
That is super cool. I think that's really important too. Like I do the same thing. I work with Galileo data, and it's stuff that, that's from the 90s, not quite the 70s, but it's still, things have changed, and you can always find little things here and there.
Oh my gosh, Galileo is like a horror story, right? They launched this probe and it had all of these sensors, and it just took all of this data, and then their cell phone on the thing broke. And so it doesn't have the ability to communicate. It's basically its broadband connection broke, but its dial-up connection didn't. So they had this tiny, tiny, tiny little straw. They're trying to send all this data back from Jupiter. It's, make sure your transmitter works.
Is that still going on? Like, is it still trying to send data? Or is that all in the past?
Yeah, I think Galileo ended up crashing into Jupiter eventually. But now we have Juno. So there is a spacecraft around Jupiter right now.
And soon we'll have Clipper, and that'll be
the Europa Clipper. Yeah, that's fun.
Well, I'm trying to figure out how to segue into this next question after all of that, because that was super cool, and now this feels just kind of sad.
Sure. Well, we'll put this one first then.
So aside from all of the calibrations and measurement uncertainties and stuff, essentially you are looking at how light from the sun affects the rest of the solar system, which obviously does. You know, light from the sun heats things up. It allows things to grow and allows us to see things. But are there any maybe really cool or really unusual ways that light interacts with the rest of the solar system?
Yeah, so I thought about this a little bit, and so I've got a couple things here. So starting with the boring ones and moving to the most interesting ones. So yeah, of course, the sun provides all of the heat and light for the whole solar system. Without the sun, it would be way, way, way colder here. And you know, the planets would go flying off in all directions if the sun actually weren't there. But you know, what's interesting is some of the coldest places in the solar system are actually closest to the sun. So at Mercury, some of the craters in the poles of Mercury have never seen sunlight ever in the history of the solar system. And so they're just like some of the coldest places in the whole solar system. And that's surprising because Mercury is so darn hot right there. And also, just as an aside, Venus is hotter than Mercury, even though it's further away because it's got that atmospheric blanket. But the cool thing that I thought of for what's something that light is doing in our solar system that people maybe have never heard of. Have you ever heard of the laser on Mars?
No.
Yeah, so okay, light from the sun charges up the atmosphere of Mars until it starts lasing like a laser. And so when you measure radio emission from Mars, you look at it as a function of wavelength, and there's one wavelength where you get a whole bunch of light coming off of Mars. And so it's an atmospheric, I think it's carbon monoxide that does it, but it's an atmospheric maser, microwave amplification by stimulated emission of radiation. That's what laser stands for, by the way, light amplification by stimulated emission of radiation. It's a laser. But before anyone ever did that with light, they did it with microwaves. And so they were originally called masers. And so there is an atmospheric maser on Mars. And if you don't really know how lasers work, it's pretty cool. You charge up a crystal with energy, basically, and so that it's glowing. But then you put mirrors on one side, on each side. So when the light goes out the sides, it just goes away. But when it goes to the mirrors, it bounces back and forth through the crystal. And so it gets brighter and brighter and brighter every time. And then you put just a little pinhole on one side and bright light can get out. So the same thing's happening with Mars. You're charging up the atmosphere of Mars with energy, and then it's emitting light, and in one of the directions, probably parallel to the surface of the planet, that is able to travel far enough through that charged medium that it gets brighter and brighter and brighter and brighter until it's basically beaming a laser out in all directions from Mars, a lot of directions from Mars. So that's like the coolest, like weird, fun fact I can think of for what just the light is doing in the solar system.
That is fascinating. I never knew that.
Yeah, the Mars maser.
That sounds like almost like Avengers type or like superhero movie type thing. Like we're gonna supercharge the atmosphere with light and then turn it into a laser. I don't know. It just sounds crazy.
Right. So like if you want to do a superhero version, if you were to take some sort of spacecraft and put it at Mars and then beam energy through the atmosphere of Mars, that would be amplified. So if you were to pick that laser frequency, if you were to pick that and shoot it through Mars, it would be much brighter once it got out the other side. Now, I don't know if you can actually destroy a planet with that or whatever you want to do, but it will have that effect there.
What Star Wars got wrong? Not using an atmosphere as the Death Star.
Yeah, seriously. And also the idea that you can take an entire star and eat that into a tiny little, like, I just want to say, like, conservation of mass is a thing. Like, if the star is this big and your little station is this big, it doesn't fit in there. That was the thing that got me with that movie. It's like, you just ate an entire star. Do you know how many millions of planets you could destroy with that? Millions of planets, probably. Millions. You destroyed one. It was not an efficient laser. I guess one of them they destroyed like 5.
But the other thing with that is that they didn't, like, they kind of just dropped it, right? Because they were able to destroy it. You know, the rebels were like, oh, let's go destroy that thing. And then it was never really brought up again. Like, that was it. You were done.
Yeah.
So,
why would they build another one of those? You know, it didn't work that time. You should make a bigger one. Make a 4th.
oh, I imagine a base that is capable of sucking a star into it takes a couple of years to build. The Alliance works too quickly, you know, so.
Yeah, so we talked about how light affects the rest of the solar system. One of your questions I wanted to address, you asked, what are some of the less obvious connections between the sun and the Earth? And so, you know, people think about like solar flares, that's totally a thing. You think about like coronal mass ejections, you know, there's active events that occur on the sun. But like, what does that do to us on Earth? For the most part, not all that much. But it can cause geomagnetic storms. So basically you can imagine like some giant ball of plasma is launched from the sun. It's coming towards the Earth. And when it hits the Earth, there's a couple things that happen. First of all, it's like a big magnet. So if you know anything about magnets, if you have a wire and you run a magnet past it, that's going to push the electricity in that wire. So you can generate current in that manner. So we've got tons of wires all over our planet, most notably the electrical grid. And so if you have an electrical grid and it's running at like 90% capacity, and one of these magnets pushes past the Earth, it'll induce more current in it. Now you're at 150% capacity and things start melting. But if you turn it off first, you're at 0 or like 10%, because you probably can't turn off everything, right? This magnet comes by, the ball of plasma from the sun, and it induces current, but now you're up to 80% capacity or something. All your wires don't melt. And so your electrical grid is safe. So the point is that if you react in time, you can save our infrastructure. And this is also true for spacecraft. If you turn it off, it's going to be a lot more resilient than if it's running, just because of that basic, like it's already running near its capacity. If you put more in there, it'll melt. So there's a couple cool points in there. Like the fundamental reason that my field exists, solar physics, at this point right now, it was mandated by Congress even as a national priority, is that we need to be prepared for these kinds of space weather events. So like right now, if there's going to be a tornado tomorrow, there's going to be a tornado watch or a warning, you know, before that. If it's going to rain, maybe we know there's going to be a 40% chance of rain. We have this knowledge. We can even tell you next Tuesday, you know, there's a 30% chance of rain. But with the sun, we have none of that. You know, we can say, oh, over the next 5 years, it's going to be more active than the past 5 years. We can even say, oh, look, that's a thing right there. Like maybe that could do something eventually. But I can't tell you the chance that that will explode. I can't tell you, you know, when it'll explode or predict it hardly at all. And so the whole field of solar physics, or at least a big chunk of it, a big part of our job right now is to gain that predictive ability. And there's a lot of different ways people are working on that. People are trying to study how does the sun work at its most basic level from the core to the edge of the solar system. And then there's people who are saying, okay, maybe we don't need to understand how it works as long as we can predict it. And so they're trying to apply like machine learning and all these other kinds of magic skills that people have that can maybe give us an idea that something might happen, even if we don't know why, or if we don't understand how the machine knows that's true. So yeah, it's a big part of solar physics is trying to say like, oh gosh, should we shut it down? And right now we've never even sent one of those alerts. Astronomy has this whole like system of alerts, and I'm pretty sure they use Twitter for a large part of it. So like something happens over there in the sky and someone tweets, oh gosh, this star is dimming, and you know, silver alert. And depending on the level of the alert, all of these telescopes will automatically slew to it. There's even a telescope in space called Swift, and its whole job is just to point immediately to whatever it is that's happening that anyone has seen. So there's this whole global network of astronomers that are currently working to see what are called transient events, things that happen in space just for an instant and then stop. And it's hard to get a lot of data from those things because, you know, they're gone after a minute. So we're working on making a similar system like that with the US and other governments, right? And if, I don't even know who the top solar physicist is right now, but like if someone were to be like, Mr. President, we've got to shut down the system today, I'm not even sure there's a pipeline to make that happen. I don't know who has a red cell phone in their office, to call the president and shut everything down. But it's definitely a national priority to build that system at this time. Yeah.
Do you consider yourself a space meteorologist?
So I'm not personally, but those people do exist. The Space Weather Prediction Center exists here in Boulder. It's at NOAA. They've got a room with people who've got videos like this of the sun in like 10 different colors, just on screens all around, and they're just like staring at them at all times. You can go to NOAA's website, and they've got a space weather enthusiast dashboard. You can pull it up and it shows you the current solar wind speed and the magnetic polarity of the wind. It shows you the coronagraphs of all the solar wind coming off. We've got all kinds of data from many, many different sources. And the biggest consumer is actually airlines. So if you want to go to somewhere in the north, let's say you want to fly from here to Russia, they might send you over the pole. It's faster. We're on a sphere. Why go all the way around when you can go over the pole? But it turns out that because of the way the poles work, that area is less protected from solar radiation and high energy particles. Because of our magnetic field, it's actually kind of funneled into that area. That's kind of what causes the auroras. So if there's going to be a major space weather event, you have to divert the planes. Otherwise, people will get radiation dosage in legally unacceptable limits. So airlines are actually continuously notified by the National Oceanographic and something Administration here. I don't know, NOAA. They're a national organization, and they send out alerts to corporations. The military cares a lot too. Like ham radio and other shortwave and longwave radios can really be affected in their range by solar events. The ionosphere of the Earth acts sort of like a mirror that you can bounce signals around the Earth with. But that ionosphere is depleted during space weather events. And so those signals will just go off into space instead of bouncing around the curve of the Earth. So if there's going to be a space weather event, you might want to hold off that raid that you're about to go make on some politically charged target that I won't get into. You might, if you want to go kill those people, but you want to actually be able to talk to your soldiers during it, you might want to wait out the solar storm. So the military actually has a vested interest in space weather preparedness as well. And like I said, and like I've said before, there is a congressional mandate right now. We have a line item for space weather preparedness. So no offense to other areas of astronomy, but unlike many areas of astronomy, solar physics is very well funded, for sure.
Just a subtle flex there by Gilly on the rest of astronomy. Oh,
no, it is nice to an unfortunate reality for a lot of astronomers. You might think, oh, you just went to like 12 years of school and now you're a space physics researcher or something. But the unfortunate reality is that a lot of astronomers worry about where they're going to get their money. Is my grant going to run out? Am I going to get funded? And I think that's a little bit unfortunate. I think that basic research should be funded more, but we do have this like, oh gosh, there it is, it's going to attack us. You want to be able to talk to your soldiers. Well, you better pay me, right? Kind of leverage. So that's nice.
So I just need to figure out how to like militarize Jupiter, and then I'm set for life, right? That's what
I mean, come on. Like, if we shoot something at Jupiter, we send it around. Now it's going really high speed. It can come back and wipe out some country, whole country. Why not? Yeah. Don't do that.
This conversation reminds me of a book that I read a couple winters ago. It's Accessory to War, and it talks about how astronomy has always kind of been used as a tool to the military, basically from its beginnings, which is kind of unfortunate in one sense. But like you said, it's also it's part of the reason why a lot of astronomers have jobs. Is because where the money is power, and if you can control Jupiter, for example, then everyone that knows how to control Jupiter has a job. So there we go. Okay, so speaking of, how the sun affects the rest of our solar system, I was curious, Gilly, do you slash are you able to look at other systems, stars that are in our nighttime sky that are not part of our solar system, look at other planetary systems and make inferences about the way that that star is affecting those systems? Is that something that you can think about even, or is that just too far away to get good
Yeah,
information on?
absolutely. Yeah, we do that. I personally don't do a lot of stellar research. So that's the difference. There's solar versus stellar. Stellar is when you look at other stars. And then there's a whole field of the solar stellar connection. And so one thing people do is they try to find sun-like stars and see how they might be different. But then there's also, there's so many kinds of stars. We have a relatively middle of the road star. It's about middle in mass, about middle in temperature, about the middle of its lifetime. It's really pretty average middle star, but that doesn't mean that it's representative of most stars either. There are tons of very, very different types of stars. There are ones that are much, much brighter, much, much dimmer, much, much larger, etc. So one that I know about and can speak to a little bit, the most common type of star in the universe that as we currently understand it, are red dwarfs. And so basically, our star is pretty big. It was able to, when it was forming, it got all of the matter from our general vicinity, and that turned out to be a moderate amount, so it made a pretty big star. But in other places, maybe there's less matter available, or it's just more spread out, and so when stars are forming there, they're just not as big. And it's easier to make more smaller stars. So that's why it's the most common kind of star. It's just, by the numbers, it's kind of easier to make those. So, okay, it's smaller, it's cooler. That's why it's red. A blue flame is hotter than a red flame. But also the weird thing that we're discovering about these stars, they're small, they're cool, but they like rotate really rapidly, I guess. And so they have very, very strong magnetic fields, way stronger, at least by proportion, than the magnetic field of our sun. So we have this 11-year cycle where we have active stuff during half of it and less active during other periods. But my understanding with red dwarfs is that they're just ridiculously active. They've got solar flares going off all the time. They've got like loops that are like comparable in size to the star itself. They throw off mass ejections all the time. I'm not an expert on this, and if you're a red dwarf astronomer, don't judge me. But my understanding is that it's a quite harsh environment, and so with smaller, cooler stars, the habitable zone, that zone where water can be liquid, is going to be much, much, much closer to the star than it is for us. So for a lot of them, like all of the planets that are habitable in the solar system might be within the orbit of Mercury in distance. But again, the star is also a lot smaller. But because they're so much closer, now they're like within that atmosphere of the star to some degree. And like the magnetic fields and the charged particles, all this stuff it's really violent there. And I think the ultraviolet radiation is another big part. So, like, yes, it's cool that there's red dwarfs, that we've found planets in habitable zones around these. It's easier to measure planets that are closer to a star just because they go around the star more often. You have to see it go around twice before you can say, yeah, that's really a planet. So if it's closer in, if it does that every 10 days, you can find that. So we have found an abundance of planets really close in to these red dwarfs. And so you might think, well, oh, that's a great place to look for life. But we just don't know at this point. It seems like if you're bathing in an ultraviolet bath and like high energy particles are coming down from space, that might just sterilize the planet. On the other hand, it might make crazy, Supermen or like weird Marvel characters, who knows? There might be space manatees. I personally like the idea that maybe there could be creatures living in the sun somewhere, and somehow they've managed to adapt to that environment. I think it's really unlikely just because of those temperatures. Most atoms don't really like to stick together really hardly at all. But in the atmospheres of these other planets, on the surfaces of planets really close to red dwarfs, in maybe like Jupiter, at some layer of the atmosphere in Jupiter, it's approximately Earth temperature and pressure ish. It's not unreasonable to think that there could maybe be something in one of these places. And just as a little aside, like when we talk about like searching for life in the universe, the only thing we know to look for at all is things like us. So all we can really do is say, could we exist there? And then, well, maybe something like us does. But you know, there could be, and I'm not coming up with this, tons of people have said this over the past 100 years, but I mean, there could be a giant brain floating in space that just thinks and exists. Who knows? Who knows? The universe has been around for 14 billion years almost, and we've been around for, well, the Earth's been around for 4.5 of those, and people have been around for like 1/1 billionth of that. So, you know, it's wild to think what could be out there.
There is a chapter in Cosmos that talks about this exactly, and one of my favorite examples that Carl Sagan gives is there's the idea that you could have this some sort of creature that lives in gas planets, right? So there's no viable surface to kind of roam around on. So instead, the transportation is, the idea is, what if there is some sort of creature that could change its buoyancy at will, so then they could float up and float and kind of sink down in the atmospheres of these gas planets, and that's how they got around, the same way we use our feet or that fish swim. And I was like, man, this is
exactly how fish do it. You know, they have a swim bladder, and they can increase and decrease that to change their buoyancy. So it could totally be. Yeah. I personally think that there's tons and tons and tons of aliens, and there's a couple series of books that go into this, but I won't tell you what they are, so I can say this without it being a spoiler. But there's this idea that one of the names of it is the cosmic shark hypothesis. So we ask, why don't we hear any other aliens screaming out in all directions? Are we alone? Like we're doing. By the way, we're doing that. And the answer might be that there's some sort of large predator, right? The cosmic shark, right? So fish don't scream out, hey, I'm here. Fish huddle in groups, fish hide when a predator comes by. We look out in space and we say, gosh, it really seems like there should be a lot of aliens out here based on what we're seeing. Like it wouldn't really make sense for humans to be the only creatures in the entire universe that we're seeing, but we don't see any. Why is that? Well, it might be that anyone who is visible gets eaten. So
is that the news that we're the shark, or that we're just ignorant to the shark and so we call out anyways?
We're ignorant to the shark.
Okay.
But the premise is, like, if we were to come into contact with another race of aliens, like we as humans can't even come into contact with other races of humans and be peaceful with them and know that they have no harm, right? If we come into contact with some other race of aliens, not only would we not know if they're peaceful, we couldn't trust them fundamentally. If they said we're peaceful, you know, the fact that they're able to communicate with us probably means that they're way more advanced than us, and they would squish us like a bug, right? So it's unlikely that we are going to be able to come into contact with anything that wouldn't be hostile, just from the basic idea that I don't know if you aren't hostile, and you could never prove that to me. So I just have to start out by assuming that you probably are hostile, and then the only way to deal with that on a cosmic sort of scheme of things is I have to eliminate the threat before it eliminates me. So again, this is sort of a plot of some books that I don't really want to spoil the book, so I'm not going to mention the author again, but it really is kind of frightening. You know, we probably, I mean, I want to find aliens. I think it'd be cool if there was a Star Trek like alien civilization, but it's probably more likely to be more of the Star Wars kind of civilization, where there's all these wild, creepy alien things and they all want to shoot you with a blaster.
Sounds about right.
But who knows, you know? Hopefully the Federation's out there.
You never know. Well, obviously, one of the things that is going to affect any of these alien races is, you know, their stars and the things that are around them. One of these buzzwords with the sun and the way that the sun works is a lot of people talk about these coronal alphane waves.
Sure.
Which is a big scary word. Can you tell us a little bit about what that actually means?
Yeah, okay, so let me just start one step back from that. The basic problem is that the surface of the sun is really quite cool compared to the atmosphere of the sun. So like you can imagine it like a campfire. Like imagine you have a campfire and you're sitting right next to it and it's pretty warm. So you take a step back because you want to cool off. But now it's 1,000 times hotter and you burst into flames. That that's not how fire works, right? Like that would be so weird, right? But that is how the sun works, because the sun isn't fire, it's plasma. And I've been reprimanded for calling it fire before. It's not fire. Um, and the reason for that is that there's no chemical combustion occurring. It's not the oxidation of a fuel that's occurring. It's not a flame. And so the surface of the sun is about 6,000 degrees. And if you go just like only 50 million miles above the surface, which is just barely above the surface, it's now 2 or 3 million degrees. That's a factor of 1,000 almost, you know? And so how does that work? How at all? You know, and so we don't know, like humanity doesn't know that yet. But we're actually in the situation where we have thousands of ideas, and really we just need to take more data and figure out which one of the ideas is correct. So the main one that I study is waves. So the interesting thing is that the sun itself, interior to the surface, is quite dense, and then exterior to the surface is quite rarefied. It's the opposite of dense, right? So basically there's enough energy in the sun that it could heat the atmosphere, but we just don't know the precise mechanism. So the way that I study is these Alfvén waves, and basically the surface of the sun is boiling. You can just imagine a boiling pot of water, and if you look at that surface, it's really quite turbulent. It's bubbling, it's moving a lot, but unlike the water, there are magnetic fields coming out of that surface. And so just like a guitar string, if you pluck it, there's a tension in the string, and it'll tend to revert back, and it'll go over, and then it'll come back and over and come back. And you get this wave, and we hear that as a tone. So that is a transverse wave. It's transverse to the direction. And that's basically what an Alfvén wave is. You've got, you know, if you're watching the video, you can see in the background here, you've got all of this stuff happening on the surface of the sun. It's boiling, it's moving, and that energy is carried up into the atmosphere through these magnetic strings, these magnetic fields. So we know that there's enough energy in the boiling to cause the heat. We know that Alfvén waves exist, and they're there. We don't know how strong they are. That's really one of the big problems that I work on in my research. It's like when you're looking through this transparent atmosphere of the sun and you're trying to see, is this thing waving back and forth? Well, if there was just one, you could like track that visually with your eye. You can say, ah, yes, that's waving. But it turns out there's like 100 of them all in a row in this transparent medium, and they're all waving along the line of sight, sort of like this. And you can't really tell exactly what's going on in there. So a lot of the work to be done is in these new telescopes that are coming on, the DKI Solar Telescope, Punch, some of these other missions, Parker Solar Probe even to some degree. They're just trying to get a measure of how strong these waves are. So what we would hope to see is that they're really strong near the surface and they get weaker and weaker the higher you go. And that would indicate that that energy is being changed from the wave into heat. And so if we can precisely measure how much those waves, it's called damping, how much the waves damp out with height, we can visually sort of see in that way where the energy is going. And so a lot of work is going into that. And my research in particular does address that question of trying to say, if we measure this, what does that tell us about these waves in the sun?
Very cool. Sorry, there's some drilling going on. There it goes. It stopped.
Sure.
On my windows. Is that so? I may have missed this. Is the idea that those waves are what could be responsible for that discrepancy, and it's cool at the surface, and then you continue outward and it gets really, really, really hot? That's a byproduct of the fact that these waves exist.
Yeah. So here's a good analogy. It's like a microwave. A microwave is a cold object, right? You put another thing into it, and then it uses waves to cause that thing to get hot. The microwave itself never gets hot. It's not like a regular oven. It's not conducting. It's not any of those other forms of heat transfer. It's sending a wave away from it, and then that wave is heating the food. And it's the same with the sun. The surface of the sun is relatively cool. It's a cold object, and it's moving. It's shaking these waves, and it's sending those waves away into the atmosphere. And then when it gets there, those waves are converted into heat in some manner via magic that we don't quite understand yet. And that's really where a lot of the work is being done right now. We can see them being generated. We know that the waves are there, but like tracking them as they go up into this transparent atmosphere and really precisely tracking exactly how they're changing and seeing where the heat's being deposited. Like you might think that it's just heated like just a little bit above the surface, but it turns out like, the sun has a radius of, call it 1. So between 1 and 10 solar radii in that whole region, heating is occurring. And it's just like that microwave. Like it's a bulk heating in the atmosphere happening due to waves. We think that's one idea. And so that's also a very related question is, where does the solar wind come from? There's wind blowing off of the sun all of the time, but the sun has gravity, right? It pulls things down. So in order for stuff to get blown off the sun, it has to receive quite a kick. And how exactly that occurs is hard to understand. Yeah, and it may be like literally photons come up and hit a particle, bounce back down, the particle's been accelerated. It could just be this wave heating causing extra pressure, which pushes things out. I think Eugene Parker has a self-consistent model that he proposed in like 1950 or 60 something, and that sort of started the whole idea that the solar wind even existed at all. And that does explain a good deal of how that's accelerated. But the precise mechanisms, it's really, just as an aside about science in general right now, 100 years ago, you could go outside and be like, oh, that's interesting. I think I understand how that works. You could go in and write something down and like, you have discovered something about how the universe works. Nowadays, it's much more in the details, right? We know that the sun exists. We know that it exists in this manner. We know a lot of ways that it could be doing what it's doing, and like which one exactly is the right answer, is kind of where we're at. And again, why is that important? Because we need to be able to predict it, right? So we want to be able to predict solar activity so that we can protect assets on Earth. And we can't do that right now at all because we don't understand the details enough.
So a big part of science is trying to make predictions based on observations, and then you can test those predictions, right?
Yeah.
And this leads to the deeper understanding of the details about a way that a particular thing or system works. And then, that's science. I'm curious how you and people in your area of research kind of do that last part of testing your predictions, considering that you don't have a star to kind of manipulate and screw around with in your lab. How
right?
Yeah.
Not in the lab, right? But I'll push back on that. We have a star. It's right there. I mean, I have a skylight in my room. This light on me is coming from that star right now, So it's true that we don't have the sun in our lab, but we've got like over 100 instruments pointed at it at all times. There's so many telescopes, spectrographs, there's assets in space, there's assets on the ground. There's a ton of data coming in. So like for me, as more of a computational researcher, I simulate the sun. So I say, if the sun were like this, what would it look like? So then I get those simulated observations and I compare it to the real ones. And if they're similar, if they're pretty close, well, then maybe I can say that my model has some validity to it. We would hope, maybe. So then I can study my model and I can say, oh, well, in this model, the temperature is doing this and the density is doing this, and that produces results that are consistent with the real observations. So I can't say that that is what's happening on the sun, but I can say that if that was happening on the sun, it would produce a similar result. And if we do that for hundreds of models from hundreds of scientists over decades, we find the models that work. And right, in some cases, 2 or 3 models could all work to give you the same observation. And that's kind of where we're at right now. That's why we have so many new telescopes turning on in this time period, is because we've come up with tons of possible explanations. I have a model myself that I made, and it, no model is a complete model that describes anything, but like I'm trying to figure out how this one thing works, and it kind of matches the sun. but it could be some other way that also matches the sun. So it's really just this game of gathering more and more and more and more data, creating more and more models, excluding the ones that don't work, finding out what does. And over time, our understanding of what's going on in the sun evolves. So 100 years ago, we hardly knew anything about the sun. Galileo looked at the sun through a telescope, which honestly, I don't know how that works. I don't know what he did where he didn't just immediately burn his whole eyes out. But he looked through a telescope at the sun and he drew these spots on the sun. And he did very detailed measurements, and we still track that kind of stuff to this day. But I mean, people just took forever to figure out what those were. Are they planets passing in front of the star? Are they clouds in the atmosphere? One person thought that they might part and you would see down to the surface of the sun and all the people who lived on it. People just, they didn't know what's going on there. But over time, we make some observation. It's like, oh, that really shows that it's not a cloud. Like we can see that this spot and this spot stay fixed relative to each other as it moves, and like that indicates maybe that it's more like a thing sitting on a surface rather than a cloud. And so over hundreds of years, hundreds of scientists, we figure out what things would make sense to explain the data that we see. So yeah, while we don't have the sun in a lab, it's actually quite close. Relative to most other stars, like we can see the details on the surface of the sun. All other stars are just like a single point for the most part. And just as an aside, we also do have the sun in labs. There are fusion reactors that people make and other things where they generate plasma, and you can study plasma locally. And what's really neat is that, I don't know how to get too much into the details here, but you can basically scale things. So even though I can't build the sun in my lab, I could build a small model sun, and some of the plasma parameters, they can be tuned in such a way that it's going to behave similarly. Like if you I don't know exactly how, but like if you up the pressure and down the temperature in exactly the right way, the balance stays the same, and then the behavior might be similar. There's these numbers like the Reynolds number, for instance. If you have the same Reynolds number, it's going to behave the same in some ways. So we can study things in that way as well in the lab, though it is not possible to remotely approach the true conditions of the sun in the lab at all.
I had a really quick question about you. We just talked about a lot about how we make models in science and then test them and verify them and say, okay, if these match up, if this model accurately predicts what we're observing, then there might be some truth to it, right? I'm curious. I feel like there's this dichotomy, at least in my head, and this could be misinformed, but there's this dichotomy in my head of striving to model, like to make a model that describes something that you've observed, or trying to understand the thing that you've observed, make the model based off of that understanding and see if it gives you the same thing back. Is that right? And how do you work on, like, what does science typically try to do? What route is the kind of standard route, if there is?
Yeah, so those are the two routes. It's called forward modeling and inverse modeling. So a forward model, you say, I think that the physics are this. If the physics are this, 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 and this, here's my model. Okay, here's what it looks like. Let's compare. So you forward modeled. You start with the physics and you end with a simulated result. Then there's the inverse model, which says, okay, I know that physics works in this way. And so, if I measure light, that light is probably telling me this about the temperature, for instance. So an inverse model, you point your telescope over at the sun, you take a measurement, and then you have some sort of iterative process. You say, okay, maybe it's like this. Simulate. Oh no, that doesn't match. Okay, change the temperature a little bit. Simulate. Nope, still doesn't match. Okay, and you keep changing and tweaking it until you get something that matches the observation, and then you can say, okay, cool. So this observation is most consistent with the temperature of this, the pressure of this, the density of this, right? And so those are just the two, both are required, and both require an understanding of the deep underlying physics, and neither of them is like agnostic to assumptions and choices that you might make. So really, people work on both sides. I personally do forward modeling. So I take the results from my advisor's simulation and this other guy's simulation, and I do a little bit of calculation, and I say, okay, this is the physics in the sun everywhere. And then I draw a line through it and say, if I looked with a telescope right there, what would I see? And I like that because I'm like super in control. There's no real data involved, so I don't actually have to be correct about anything. Like if I get it wrong, it's like, it's not wrong, it's what I modeled. You know, there's no such thing as wrong. I mean, there is, but like in a way, like what I produce is the results of my model based on what I did. And if I can justify and show what I did, it's interesting regardless of whether it matches the sun exactly. So like there's a lot of stuff that I do where it's like, I'm not even necessarily trying to match the exact result out of a telescope. I'm just trying to say like, what would happen if you doubled the temperature? You know, and the sun isn't doubled in temperature there, but I have the knobs where I can say what would happen if I do this other thing. And by turning those knobs, we learn about the way that those knobs affect observations. So then when we look at the observations and we say, oh, I'm getting this, then you have more insight to make those inverse observations. I just measured this based on these 3 forward models. I'm pretty sure that that kind of thing interacts with the measurement in this way. And so now my model is saying that that exact sunspot today on December 12th is probably this temperature and pressure, you know? So they're definitely both, it's a 2-pronged approach. And I'll go on a little bit of a side about this. There's this whole thing called research to operations and operations to research. It's a feedback pipeline. And so we've got operations, which are those space weather prediction people. And they're sitting there and they're like, okay, I don't necessarily need to understand how this model works, but I've got this box. And when it beeps at me, I know that I need to tell NASA that there might be a solar flare or something, right? So not to put those people down in any way, I'm sure that they do understand the models, but in a way, they're trying to create a system that is operational. So it's less important that they're able to know exactly the temperature of something, and it's more important they can provide a probability that that's going to be an issue for airline pilots or something, right? So operations has a very different set of goals than research, right? But the researchers are trying to make better models all the time too. So there's communication between these two communities. Operations says we're not able to predict such and such with a good enough, well enough, you know, and then the researchers try and do that. And there's feedback between them, and it can be difficult sometimes to get a new model into production. But yeah, it's a whole thing, and there's way more industry partners and government interests and stuff in the operations side than you could ever imagine. Really, it's a big deal. So I've started like learning a little bit about R2O and O2R is what they call it, or R2O2R is the feedback. But yeah, there's just so many different people with different concerns, you know. So I'm just working more on basic research, but one day I really want to do more like the sun-Earth connection specifically with space weather. But by sticking with research at the beginning, you know, I'll be able to be the scientist, sort of mission specialist kind of person, or instrument scientist or something like that. And that's going to be cool.
So another thing that we wanted to ask you about is this idea that, you know, everybody always teaches us that space is very empty. You argue otherwise. You're shaking your head right now. So can you kind of enlighten us on the non-emptiness of space?
Oh my gosh, yeah, absolutely. And I've given an hour-long talk of this. I've given this talk in a planetarium. I've given this to alumni who have argued vehemently against me. But okay, I've got 3 prongs to this argument. Here's the very first one. Let's draw a sphere around the Earth. How much of the matter in the universe is inside that sphere versus outside that sphere? The answer is there's almost nothing inside of it. The Earth accounts for like nothing % of the universe, right? So even just from that basic argument, everything in the entire universe is in space except for Earth, right? So just from that, I mean, everything is there, literally everything except for Earth. So
That reminds me of what we learned in chemistry, which is you have your system and the surroundings, and together they make up the universe.
right, yeah, yeah. And so the Earth is just this tiny, tiny, tiny system. So that's one prong, way more out there than there is in here. Another prong, it's just about scale. So you've heard this like, okay, if you zoom in on an atom, it's mostly empty space, right? But if you hold an anvil, if I hand you an anvil, that doesn't matter that the atoms are mostly empty space. You will drop it on your foot probably and hurt yourself, right? It doesn't, the fact that if you zoom in really close, it's technically mostly empty space, doesn't give you a feel for the true nature of the anvil, right? And so it's the same with space. If you, a person, go out into where space is and you look around into the middle of the solar system, you're going to be like, yeah, there's nothing here. Like the nearest Wendy's is so far away, you know. But if you take the solar system and you look at it on this scale, like here's Pluto. If you just hold out your hands and you look at it in your hands, the whole solar system, yeah, you're going to have the rocks and the gas giants and the sun that are the main things in there. But, you know, if you're watching the video, there's all this stuff coming off of the sun all the time. There's solar wind flowing out through the solar system. It interacts with the magnetic fields of the planets. It causes auroras. It interacts with the planets with no magnetic fields. Mars has had a good deal of its atmosphere just literally blown off into space. All of that atmosphere of Mars is now in space. You know, the solar wind, it goes all the way out to the edge of the solar system where there's an actual boundary called the heliopause. And so the solar wind is flowing out and then it hits a wall that is the interstellar medium. So between all the stars in the galaxies, there is this ocean of hydrogen. And again, if you zoom out and look at a galaxy, when you look at it, you don't see a bunch of individual stars. It looks like a big soup, right? Like a galaxy looks opaque because of all that gas in it, right? And yeah, if you personally stood in the middle between two stars, that would be boring. There's no cell service there. But seriously, when you zoom out, like stars, as they're moving through the galaxy, they leave a wake behind them in the same way that boats do. They've got like when a boat goes through the water and it's got that like pile up at the front of the boat, we call it a hydrogen wall at the front of our solar system. And then even galaxies themselves, like you think of a galaxy as this disk, right? Well, what if I told you that like if the galaxy has a radius of, again, 1, up to like 10 to 100 galactic radii outside of the galaxy, there's this huge sphere of gas. So all the stars in the whole galaxy are blowing off their solar wind, and that solar wind flows out of the galaxy until it stops because of gravity and turns around and falls back in. And so there's this cycle of gas leaving and falling back into galaxies, and the infalling gas triggers star formation. It's a real big active effect of this stuff. And even between the galaxies in the far distant reaches, I mean, there's still a couple particles per cubic kilometer or something, whatever it is. There's nowhere that you can go in space where there isn't anything at all. And so that's just about matter. I mean, you know, if I went to the middle of space and I cut out a cube, you know, what's going through that cube? Light from every star in the universe, from every direction, is going through that cube on its journey. Cosmic rays and particles from every direction are going through that way. Magnetic fields, if I put a magnetometer out in the middle of space, it would read a value. You know, maybe it would be too low a value for my magnetometer, but there would be a value there. And then even just at the most fundamental level, like space itself is an object. If you imagine a bucket and you pour water into the bucket, it's not just water magically floating there in space. Like there is a bucket holding the water. And it's hard to imagine this with space itself, but like we couldn't be here if there was no space to be in, right? And matter and space interact in a lot of ways that I'm not going to get into with general relativity. But the idea is like you could like cut out a piece of space and hold it and say, this contains energy, right? And so in so many ways. There is just nowhere and no way in which space is empty. The only way that anyone could ever say space is empty is if you zoom in really close, it's mostly empty, just like they say with atoms. But nobody says an anvil is mostly empty, right? So in my opinion, space is full. You know, most of the stuff in the universe is out there compared to here. But then even just on a basic level, if you look at something on its own scale rather than super zoomed in, it's dynamic. There's stuff happening there. I've got tons of images. If you go to my website, gilly.space, I have a whole page and presentation and all this stuff about this topic, and you can look at those. But yeah, oh my gosh, it's so active. And then the final thing is like, we have spacecraft just floating out in the middle of space, and they're measuring particles and fields and all of that stuff in situ. So if it was empty, they wouldn't have a job. And so if space were empty, you're arguing that, you know, NASA is just wasting money to send these things out there because there's actually nothing to measure. And, you know, I was going to say the government doesn't waste money like that, but that's not true.
Well, and that's to say nothing of like dark matter or dark energy or things that we don't know how to interact with yet.
Absolutely.
God knows what's out there.
Matter that we see as matter that makes up stars, galaxies, and people, that accounts for 4% of the total energy in the universe. 4. Dark matter is like 23%. Like, I personally think that like going out into space to explore is probably going to end up not actually being the way that we go. We're going to realize, like, because of the speed of light, I mean, it's going to take hundreds and hundreds of years to get to any of these other places in meat space, in real space. But like, this is me just being a sci-fi nerd here, not speaking from my position as a scientist, but I kind of feel like we're going to discover like the mirror universe or something, right? Like the like dark energy and all that, maybe it's just some vague particle just floating around and who knows what it does. But it also could be like the real cool people universe where all the cool kids are hanging out and we're just like this infant race who hasn't graduated to the knowledge that we're living like in Flatland right now, you know, if you've read Flatland. And again, that's not coming from my place as a scientist. We really have no evidence to support that at all. It would make a good book. But we also don't have evidence that excludes that from being a possibility either. And so, you know, that's not a great argument for something being true.
I would like to present some evidence that excludes that from being a possibility, which is that you say, well, there could be this mirror universe where all the cool kids hang out. That's impossible because all three of us are right here, now.
We're not
say that there is no other universe where the cool kids hang out because we're right here. So
yeah, and humans, you know, I guess you mean probably us particularly, but
specifically, yeah, Tara, Gilly, and I, yeah, and John too, yeah.
But we're not, as species go, we're not particularly considerate to the other species in our vicinity. You know, that's why the Federation doesn't want us yet.
We must grow. I'm curious, and I know that we're kind of coming up on where we would typically say, okay, this is our time, but really quick, Gilly, what made you seem to be very passionate about this idea that space is not empty. Like, that, to me, you know, I totally see what you're saying, and I'm like, yeah, that makes perfect sense. But it doesn't like grab me like viscerally, like it seems to like be a really important part of the way that you think. Why is that?
Yeah, you know, like, how do you make a good analogy? It's like, you know, I study space, right? So hearing like, oh, space is mostly empty, I mean, A, it's just wrong. And so as an educator, I'm like, no. But also, like, you know, I want people to be excited about space. When most people think about space, they think of this cold vacuum. They think of this unfeeling, uncaring place. You know, they don't think of like this exciting, dynamic environment that we can go to or we can study. You know, like, literally, you could be a person who just studies the emptiness between stars. There's a good Isaac Asimov quote about that. And like, that's just really exciting to me. Like, I really want to get that idea. Like, everyone's heard that space is empty. What the heck? Like, who invented that idea? Like, why are we telling every kid ever that space is empty? It's not. A, but B, that's boring. Like, at least tell them about the cool things in space. You know, most people think about like there's stars and planets. Those are one of the many, many, many kinds of things out there. But like people don't know about nebula and all these other interesting things, globular clusters, open clusters, galaxies of all these different shapes and morphologies. They don't know that the sun is an active living object that's always changing and doing things. And I just kind of think that it propagates this idea that Earth is the center of the universe. You know, like we're not. We're not all that special here. And Earth isn't even the most interesting place in the universe. It's got people on it. People are kind of awful in a lot of ways, but you know, they're great in other ways. And I do support the, you know, idea of humanity spreading out into the stars and stuff. But I guess like when I think of space, I think of all the sci-fi I've read in space. I think of all the stuff in space. It's very exciting. It's very exciting to me. And I think a lot of people are kind of turned off from space in some ways by that space is empty mentality. And I mean, I get it. Like, actually, of the sciences, astronomy makes the pretty pictures. So the public does tend to be pretty interested in astronomy in general. But you know, it just seems wrong to me. Like, who thought up the idea to teach every school kid that space is empty? Like, that's like a personal injustice that I'm working to fix in the world. If I can tell a million kids how not empty space is, you know, that would be great.
Well, hopefully there are maybe a million kids listening to this.
Yeah, that would be excellent.
Fingers crossed. Maybe 30, maybe a million, somewhere in between, probably.
Well, and the great thing, you know, a thing that I like to do in my life, I'm really interested in creating things that outlast me. You know, I like to create outreach organizations and clubs and then set up a structure where it will continue. We've got this Science Under the Dome series going on at the Planetarium, and I'm going to graduate soon, but I've really made it into an institutional thing by creating all this documentation. And yeah, so the same with videos like this. Like, yeah, 30 people will listen to it this month, but over the next 100 years, who knows, right? We live in an age where this will live forever, probably.
I think so. And I think that was an excellent way to sort of wrap up our time here. So thank you so much, Gilly, for joining us. That was fascinating.
Thank you so much for having me. I really enjoy all of these kinds of experience and just talking forever about whatever it is. So you know, thank you so much for giving me this opportunity.
Yeah, thanks for coming.